Good morning to all of you. This is the last day of the e-learning session. So this morning, we will talk about determination of elements in soil using ICP-OES. And in the afternoon, we have another session on the determination of energetic materials. So today, the session will be given by myself and by my colleague, my analyst, Philippe Beutels. Philippe is also the one who will give you the training in person when you will be in our lab. Okay, so let's start. So this is more or less the outline of what we will see in this session. So first, I will give a general introduction, some considerations about presence of elements in soil, how you need to determine, and then I will go a little bit deeper in theoretical background of the acid digestion and the ICP optical emission spectrometry. Thereafter, the practical training will be given by Philippe. I just made a link to all previous sessions related to, for example, A3 on soil available phosphorus, potassium, where Jill always made this nice figure of a flame representing the ICP-OES. So therefore, we consider we took a little bit more attention to this part as the determination of elements. So it's not about only the total, but you can measure with ICP-OES also a lot of other, for example, soil available micronutrients or even soluble sulfate. So just as a reminder for you. So elements in soil. So if you look at the periodic table, but it's maybe a strange way of looking at it, you can see the elements and their relative abundance. So what I want to show here is that basically all elements which are available in our periodic table have some geological origin and exist in soil. This is always something you must consider when assessing contamination, especially for elements, as compared to, for example, organic substances, which are mainly man-made and which should not be present most often in our nature or environment. On the right-hand side, you see a figure here showing that indeed you can have some locations with elevated levels. For instance, this is cadmium, where this has been caused, for example, by contamination or soil pollution. But this is basically always on top of the existing concentration, which can also vary depending on your geological situation. Something you must remember when we talk about the determination of elements in soil, we talk, for instance, about cadmium, we talk, for example, of lead or zinc, but of course, this is not how these elements are present in our environment. You can see here some main forms of chemical, for example, cadmium, how it is present in the soil. So it's not there as elemental cadmium, but it can be in a dissolved form in the liquid phase or precipitated as, for instance, as cadmium carbonate or cadmium oxide. The same holds true for all the other elements. And basically the same holds true also when you would determine elements in water. So also here, they are most often complexed or chelated to some, for example, organic complex. So always consider this. We talk about cadmium, but basically it is present in a form in the environment. In order to characterize these different forms during the last decades, a lot of what we call sequential extractions have been made. For example, to determine only the exchangeable fraction, because these are available for plants. This is what Gilles has been discussing. Also, you could consider only to see what is present on the carbonate fraction, maybe the reducible fraction, the oxidable fraction, or the residual fraction. So for all of these different fractions of the elements in literature, some operationally defined methods and extractions have been described. For example, if you want to determine the acid-soluble fraction, you could consider using acetic acid to extract your soil. I give you this overview just to show that depending on what kind of extraction you will use, you could determine maybe different forms of elements present in your soil. how to quantify, determine elements in soil, because that's most often the question we get. Can you determine what is the concentration of a certain element in the soil? So I think the first step is, of course, always sampling. There it starts, but this is not what we will consider today. Our first step in the lab is the sample pretreatment, and this is really important. So we always start with drying and sieving, and especially also for ICP, a ball mill to get the particles less than 250 micron is necessary, since we only digest a very small portion for the analysis. We can talk about direct and indirect methods for the determination of heavy metals in soil. A direct method, for example, you can measure the soil as a powder or pressed in a pellet, and there you could use, for example, energy dispersive X-ray spectroscopy. When we consider another method, the indirect method, then you always need to do an acid digestion. An acid digestion can be done in a microwave oven, a high pressure temperature, temperature oven, a heating block, or also some other configurations of high pressure temperature heating block. That here you make the soil, you convert it to a solution. And then in the last step, step 3, is basically the determination of elements in the solution. This can be done by AAS, atomic absorption spectroscopy, by ICP-OES, which is optical emission spectroscopy, or, for instance, ICP-MS, which is mass spectrometry. Coming back to the acid digestion, this is basically one of the most important steps, and because you need to know that there are different of mineral acids available, which all have their specificities. For example, if you want to dissolve the silicate matrix, you have to use hydrofluoric acid, because as you can see here, the hydrofluoric will attack the silicium and will dissolve it. So that's an important notice, that what we call elemental and matrix compatibility. This means not all elements have the same stability depending on which acid you use. And that's always something you should consider. Especially because the acid digestion mostly used for the determination of elements in soil is what we call aqua regia digestion. And this is what is stated here, a pseudo total concentration. So I took the graph again, and basically you can see that when you determine the aqua regia fraction, this is basically what you determine. And therefore it's called the pseudo total, because you're not measuring the full concentration of elements. If you want to determine the total concentration of elements, you definitely need to add hydrofluoric acid, because there you always dissolve the silica matrix. So just to summarize a little bit on the different acids, the nitric acid destroys the organic matter and oxidizes sulfide material if available. So the aqua regia is a mixture of hydrochloric and nitric acid, and this forms also this very strong oxidizing agent. So aqua regia is considered adequate for dissolving most elements, sulfates, sulfides, oxides, and carbonates, but only provides, as I said earlier, a partial extraction for most rock-forming elements and refractory nature. So therefore, we call it pseudo-total concentration. For example, if you would use aqua regia extraction for some elements like cadmium, copper, lead, zinc, this will be almost equal to the total, but for some others, like chromium, nickel, and barium, you will see a clear difference between an aqua regia digestion and a total digestion. For the determination of the total of these, you definitely need to use HF. However, as I said, aqua regia digestion is internationally accepted to measure concentrations in soil, admitting that a fraction of elements that not extracted by this method is always not available for biological uptake. So basically, you can consider the aqua regia as some kind of worst case concentration that could be made available in the end to the soil. Also, I made a note, hydrofluoric acid is a very dangerous acid, so always use very much precautious when handling HF. That's also one of the reasons why HF is sometimes not used in a lab. Okay, just to illustrate the pseudo and total concentration. So for pseudo concentration, you do an acid digestion, for instance, with aqua regia, and you measure it with ICP-OES. Another example of
Sorry,
total could,
Christoph.
yes.
Christoph, translators asked to slow down a little bit for the translation purposes.
Okay, thank you for warning, Sergius.
Thank
Okay.
you.
So for the total concentration, you can, for instance, use XRF, and this will also give you an indication of the total amount of elements present. In the figure, these three figures here, I have shown on the one hand, these have been done on soil samples that we received from Ukraine, a comparison between the pseudo concentration of copper and the total concentration. For instance, for copper and zinc, you will see there is a fair good correlation. So meaning what I said earlier, that aqua regia will give you more or less the same concentration as total. For chromium, you can see a very clear difference. You can also see it at the slope, which is only half and also very much scattered. So chromium is definitely an example where the total concentration is not equal to the pseudo total concentration. Some quality assurance topics. First of all, so mainly when determining elements in soil, there are three steps. The first step is the sample pretreatment. So as I said, you need to mill the sample. And of course, you need to clean the milling device between each soil sample to not contaminate or have cross-contamination. Also, take care that the material of the milling device can contaminate your sample. So that's also something we have observed. The second step is the acid digestion. Here we said use ultra pure acids and check contamination by using procedure blanks. So the quality of your acid will also determine how good and what the level is in your blank. Also here, we spend a lot of time on cleaning digestion vessels prior to use, or alternatively, you can use disposable vials tubes. This is also something we use in-house. In the last step, the determination, of course, use certified reference materials or other reference materials to verify your calibration. Also check regularly recovery rate of spiked samples and use control charts and other measures to check your quality. This figure just represents that a lot of time mostly is done on the sample preparation, while basically the analysis itself doesn't take that long, but also the data management and interpretation of your data is also something you will spend much time on. This will also be shown by Philippe afterwards. Which standard methods are available? I summarized the methods which are in use, but mostly for today, we will focus on the ISO determination of digestion of aqua regia soluble elements, and also the one using ICP-OES. Coming back first to the acid digestion. So in the standard for the acid digestion, basically three methods are described. First method is, as you can see here in the picture, a reflux of your soil in an aqua regia digestion solution for 2 hours, followed by filtration. A second one, represented here, is a heating block, which set at a temperature of 105 degrees. And also here, your soil is digested for 2 hours. A last one is the microwave digestion. Here, you use a temperature of 175 degrees, and you will do a digestion for 10 minutes in a closed vessel. Coming a little bit back on why the acid digestion is done and what is the need for the temperature. So in this curve here, you see the vapor pressure of the most different acids that we used. So most acids have, let's say, a boiling point in the range of around 80 to 120 degrees. For example, if you have a pressure raise of 25 bar, this would mean that your vapor pressure of nitric acid would be 240 degrees. Now, basically, what is the importance of the temperature is that increasing the temperature will also decrease your reaction time. So in order to have, for example, this is like just a comparison using the Arrhenius equation, to convert for at 100 degrees at 2 hours, this would be more or less the same from a kinetic point of view as using 2 minutes at 160 degrees. So that's basically the relation between temperature and reaction time. Why it is important? Because you have, I would say, two methods that are mainly used in laboratories for doing the digestion. The one is a heating block, as situated here. The other one is the microwave. What are the pros of the open vessel? In this case, I think one of the main advantages is you can simply use disposable vessels. This means no cleaning. You do the digestion and you throw it away. Then also it is relatively easy to add reagents. You can use relatively large sample amounts and it gives you a very high throughput. What are the minus? Well, of course, it is an open system, so the limit of the boiling point. It's relatively low temperature, 105 degrees. You might have danger of analyte loss, as it is an open system, and also incomplete digestions. Also, as represented here in the figure, the heat transfer is conductive. It is slow and mainly not energy inefficient. So you can see here, this is your tube. So you can see, because the heat is coming from the outside, it needs to go slowly to the inside. So it's a conductive heat transfer. When you look at the microwave, here you can use high temperature. You can have a complete digestion. It's a fast method because the reagent absorbs microwave energy. So you can see the heat transfer is much better in these kind of systems. So also you can see this is a direct in-core heating. It's instant in-off. So if you shut down the microwave, it directly stops. While here, of course, it needs to cool down. You have reagents and no analyte loss. What's the contra of the microwave? You have limited sample weight and, of course, as you can see, a higher equipment cost. These were some general considerations on the digestion. Let me move now to general considerations on the ICP-OES. So basically, in this graph, I summarized the methods or the instruments that are available for the determination of elements. I will focus today on the ICP-OES because, as we have seen, most laboratories in Belgium and I think in Europe for soil analysis use ICP-OES, and the reason why I will discuss this later on. I think most important to know is that the ICP-OES allows simultaneous multi-element analysis. It has a wide dynamic range, and it can offer also high throughput. As an example, if you would digest 1 gram of soil in 50 ml digestion solution, you will have more or less detection limits in the range of 0.1 to 0.05 ppm, which is acceptable for most of the elements in soil. Here you can see which elements of the periodic table can be measured with ICP-OES, so showing the multi-element determination. And of course, some elements are more sensitive than other ones, but most of the time it is sufficient for the determination of elements in soil. So once again, I have shown here the slide. The only remark I have here is mercury is not so sensitive to be measured with ICP-OES, especially at the concentration levels observed in the environment. So if you want to determine mercury, there are other methods available. For example, one is the direct analysis, where you can use your soil in a boat, ceramic boat, and then do thermal decomposition and atomic absorption. This is one possible. Another is also to digest it, and again, go, for example, to ICP-OES or cold vapor AAS, which is most often used here as it is relatively easy and cheap instrument and allows a very sensitive determination of mercury. Okay, then we come now to the different parts of the ICP-OES. So I will guide you through the different parts. Basically, it consists of a sample introduction, the excitation, the spectrometer, the detector, the data processing, and the results. In this graph here, you can see basically the concept, how it works. So you get a peristaltic pump, the nebulizer, then your aerosols go to a torch, they emit light. This light is then separated in a polychromator, and all this light is then kept on a detector. So the remaining of the presentation of myself and Philippe will now be dealing with the different parts of what you have seen in this graph. So what is basically ICP, or what does it stand for? So ICP is inductively coupled plasma. So, and what is a plasma? Basically, plasma is what you can call it, the fourth state of material. Besides water, solid, and gas, you have a plasma. And this is a collection of charged particles. So you have an equal number of positive ions and electrons in your plasma. In our case, it is an argon plasma. So this means we have argon gas that is ionized. Why it's inductively? Because we make use of a radio field, of a radio frequency field. This is applied to the load coils, and this basically induces an oscillating alternative current between the RF coils and plates. And this makes sure that your electrons bounce one side and the other, collide with your argon, and there your plasma is formed. So this is also what I said. And then mainly why we use the ICP is that basically we want the elements in the sample to be excited or ionized in order to emit light, because that's basically what we want to measure, the light that has been emitted by the elements. And therefore we call it optical emission spectrometry. This is basically how it looks like. So here you have the plasma. So this is what we call the torch. So what is the function of an ICP? Well, of course, as I said, you want to know which elements are in my sample. Every element emits specific light as the sample processes through the sample. So this light is then separated and detected according to its individual and very specific wavelength. This wavelength measured in nanometers is what distinguishes one element from another. For example, lead will emit an intense line at 220 nanometers. Also, we not only want to identify, but want to do quantification. So by doing so, what is the function there is we want to know how much of an element is present in my sample. And there the quantity is proportional to the intensity, so the brightness of each individual emission wavelength. The greater the intensity, the more of that substance is present in your sample. The lower, of course, the less. And then you need, of course, a comparator, so basically a calibration to know versus unknown. So let me go a little bit more in depth of what is atomic emission spectrometry. So basically, what you do is a discrete amount of energy released in the form of light, a photon, equal to the quantity of energy initially absorbed by an atom had elevated a valence electron from its ground state energy level to an excited energy level. So here you can see more or less the process that will happen when your aerosol goes into the plasma. So first of all, you get your atom, which can be excited and here will send out light, or even you can have an ion, and this will can also be excited and send out some light. when the ejection of this photon occurs, so basically after that, it returns to a ground state. And basically, we are talking about valence electrons, also known as bonding electrons. In the following graph, this is an example of basically what happens for lithium. So if you would consider the lithium atom, so basically you have what we say 3 protons and 3 neutrons. Then you have the 1s, which contains 2 electrons, and also the 2s orbit, which contains, in this case, 1 electron. So this is basically the ground state of lithium. When we add here the plasma, so if you introduce the lithium in the plasma, basically what we will have is an energy transfer. So what will happen first is that basically the electron of the 2s will be sent out. So it will go to another orbit at a 2p, for instance, in this case. This is basically the process of atomic absorption. A photon is absorbed by an electron and it goes to another orbit. There we have what we call an excited state. So lithium is no longer in the ground state, but in the excited state. What will happen then? Of course, once in the excited state, as it's not stable, it will return back. So here the electron goes back from the 2p to the ts orbit. And what it will do is it go back to the ground state and it will emit light. So, and this light in the energy photon is basically what we measure with the atomic emission. So at a very certain wavelength. In the case for lithium, this is about 670 nanometers. Also, other lines are emitted by lithium in this case. Why it's important? So this is basically the element structure and emission. So wavelength and energy are correlated as shown in the following equation. So basically the energy of the photon is related to the wavelength, and the wavelength is very specific for each element. This just another figure to illustrate. This is an energy level diagram of sodium. You have the ground state, you have the different orbits. As you can see, depending on the element, you will have very discrete energy levels, which are very specific for each element. So this means that when you expose an element to high temperature, and energy, you can move electrons to higher orbits. This is what I have shown in the example of lithium. In many situations, however, the temperatures are high enough to also remove 1 or more electrons from the atom. Then you have an ion, which also can be in a ground state. So you can have atomic wavelengths and you can have ion wavelengths. So both can be excited and both can send out light. Okay, this was more or less the theory behind the emission. So how does it come that elements emit light? Now we go to the ICP-OES. This is basically the instrument that has been developed to measure the emitted light. First, and I think one of the very important parts of the ICP is the sample introduction. Because the sample solution, the digestion in our case, cannot be put into the energy source, the plasma directly. The solution must first be converted to what we call aerosol. Yeah? And the function of the sample introduction system is to produce a steady state aerosol of fine droplets. So that's the main function of the sample introduction. How is it done? There are different ways to do it. This is just one example here. So you have, for example, a glass concentric nebulizer, where basically you push argon together with a stream of your liquid to this kind of device. And here you can see that an aerosol is formed. There exist a lot of different nebulizer, depending, for example, if you need HF resistance or if you would like to have more total dissolved solids and not clog your system. So different commercially available nebulizers are available. A second part is you nebulize it in a spray chamber. So what is the function of the spray chamber? Two examples are given here. Is basically you want only a selection of droplets to go to your plasma, because the large droplets would use more energy of your system, so there would be less for excitation. So you will not like to have large droplets. So basically what the spray chamber does is to only let the smaller droplets go into the plasma. And with small, I mean, for instance, less than 10 micron, and cutting off all the largest. This means that often only 2 or 3% of what you actually insert as a droplet will finally go to your plasma. So, but that's no issue because it's still sensitive enough. So these are other examples of spray chambers. And just to remind, why does the aerosol diameter matter? So basically because it affects your transport efficiency to your plasma. So depending on the type you use, you will have more or less aerosols going to the plasma. As we will see later on in the plasma, you will have desolvation and vaporization of your droplets. So depending on your diameter, this will all influence the processes in the plasma. And the aerosol diameter itself is influenced by the density of the solution, the viscosity of your solution. So depending on the acids you use, you might have different aerosols formed, also the type of nebulizer and the type of spray chamber. So just to summarize the sample introduction, there are different nebulizers and spray chambers and combinations. The smaller droplets are preferred because they have faster desolvation and vaporization. Basically, also, you need to know that no signal arises from droplets which are higher because they don't have the time enough to get atomized and ionized. I think a very important, therefore it's marked here, is that a lot of interferences occur at the nebulization. So please always make sure that your system is in place. And why is this important? Because as I said, depending on the acid you use and the system you use, you can have difference in surface tension, density, different aerosol diameter. So this is important that you must matrix match standards to samples as much as possible for best accuracy. This means that your calibration solution must be in the same acids as your sample. That was about the introduction of the sample. Then the next step is the excitation source. So the aerosol goes directly into the center of the plasma, and there the energy is transferred to the aerosol. Now, the main function of the energy source is to get the atoms for the elements of interest sufficiently energized such that they emit light. So that's the main importance of the excitation source. Here you see the plasma. Most often, an aerosol, it only takes about 12 milliseconds to go from here to there. So it's really fast process. What does happen? You have your aerosol, it gets dissolved very rapidly, vaporized, atomized, and in some cases also ionized. So, and those two are the ones that emit light. When we have a closer look to our plasma, you will see that what we have here more or less an atomic region and an ionic region. So in this case, most of the light that is emitted is coming from this part, an atom that has been excited and sends out light. Here in this part, the atom may have been ionized because it has received more energy. Also, an ion can be excited and send out light. Why I show you this is because most often the plasma can be viewed in two different perspectives. We have what we call an axial view and a radial view. This is illustrated here. is this is your plasma, and you look from top to bottom. This is what we call an axial view. This means over the full length of your plasma, you collect the light. In a radial view, you only watch at a specific height and a specific region of the plasma. So this is shown here one more time. You got your plasma. An axial view collects over the full, the radial only at a specific height. So axial view will give you the best sensitivity because, of course, you measure over the full length, but it comes to a price. You also have enhanced interference effect, maybe also increased plasma suppression. So it can be used especially for clean aqueous samples. Radial view has fewer interferences, but here it is less sensitive than axial view, but for some major elements, this is no issue. It is better for high concentration wavelengths or heavy matrix samples. Also, in some cases, this mirror can be adjusted to specific certain regions of your plasma. Then we come finally to the spectrometer. So once the atoms in a sample have been energized by the plasma, they will emit light at a specific wavelength based upon the atomic structure. Therefore, no two elements will emit light at identical wavelength. And that's now what is the function of the spectrometer, is to diffract the white light from the plasma into individual wavelength and spectral orders. So this is shown in this graph. Basically, we have your plasma, and then the spectrometer through different gradings and entrance slits will finally convert the light into different individual wavelengths that can be measured. That's the function of the spectrometer. And then, last but not least, we have the detector. The detector, that's basically where the separated light will fall on. So the intensity of a given wavelength is proportional to the concentration of the element present in solution. Yeah, and the function of the detector is to measure the intensity of the element-specific wavelength. Here you can see different chips that are used, different detectors of different manufacturers where light falls on, all considering of different pixels, and each pixels can then be used to measure the intensity of a specific wavelength. If we now look, for example, at the detector, you can see here that it falls, and you can especially here see the first order wavelengths giving you a lot of light. Each pixel corresponds to an associated wavelength. And then, of course, you need your software to relate each pixel to a certain element. In this case, you can see the different peaks corresponding, for example, to sodium, calcium, and so forth and so on. So this illustrates that on the detector, your light is separated into different wavelengths, and each wavelength and the intensity thereof can be used to do a calculation of the concentration. So I think this first part, I would like to stop here. This is the theoretical session. And then I think before going to the next session where Philippe will more elaborate on the practical ICP, I just wonder if there are any questions so far. And I'm sorry, I was maybe too fast for the interpreters.
I have a question, Christoph. Why mercury behaves differently in ICP-OES?
It has to do, there are two things. It behaves the same, you could say, but the concentration levels you want to determine are rather low. And the ICP-OES is not sensitive enough. With that, I mean, you can maybe measure 1 or 2 ppm mercury, but if you want to, if you have, for example, an environmental quality standard of 0.5, this is not enough to check if you have contamination. So the issue is you can determine mercury, but it's more that it's not sensitive enough with the ICP-OES.
Thank you.
All right. If there are no other questions, I would suggest again to have like a small 5 minutes break so that we can switch speaker and we see each other at 46:47 to continue with the second part of the presentation. All right. Welcome back. Maybe to first answer, Sergius, your question a little bit more. We have done in the past mercury determination by ICP-OES using hydrate generation. So you can also use hydrate generation systems coupled to your ICP-OES, which will enhance very much your sensitivity. But then the issue is that the ISOP-OES is a very expensive detector if you can only use it for mercury. And therefore, I think most often, labs used the cold vapor AAS system because it's relatively cheap and really dedicated to mercury. So there are ways how to circumvent and improve the sensitivity, but I think in routine, I don't see it often used. This as a complement to your question. Yeah.
It would be quite interesting to learn from participants here whether someone using ICP-OES and their experiences, perhaps translators can ask this question, and let's see in the chat if someone is already experienced with this equipment. Thank you.
I only noticed that there was the method for determination is indeed in Ukraine, the Aqua Regia. So that's, I think, similar. But then I observed that the atomic absorption, which is indeed also a very good method to determine, but there it's more mono-elemental.
So you have to calibrate for each element and analyze it individually for each element.
Yes. So you analyze each element individually, and I think that's the main reason why for soil analysis and environmental analysis in general, ICP systems are often preferred because you can determine simultaneously. And I think the other one is you have a very wide dynamic range. With that, I mean you can measure, from instance, from 1 ppb to 1 ppm or even larger using a calibration line, while with atomic absorption, you have more or less smaller working ranges, which you will also need then to dilute, for instance. So, but that's just a practical things. I don't see anything appearing in this chat, but indeed, maybe for later on and to improve the discussion, it could be good to have an idea if people in the audience have experience or are using ICP-OES. So please put it in the chat.
Yeah, to my understanding, when we looked at the soil laboratories in Ukraine, we did not identify any labs in the country who is in possession of that instrument or capable of analyzing materials with it.
Yeah. Okay. I would suggest let's wait what appears in the chat, and then meanwhile I would suggest that Philippe, you continue the training session. And then I think, as I said earlier, Philippe will be the one who will also give you the training in person when you come to our lab. So I think you summarized the different steps that you will then also show when you give the practical training. So please, Philippe, the floor is yours, and try to speak slower than myself.
Okay. Good morning, everybody. Wait, I seem to have a problem with the slides. Okay. So welcome to the part where everything seems to work, but nobody knows why. Some words about the practical training of the aqua regia digestion of soil. As you know, ICP-OES is an analytical technique that is based on the measurement of solutions. Now we start from a solid soil, so we have to convert it some way to a solution. And we do that by using aqua regia and heat. So the result is a solution and a residue, because the aqua regia digestion is not a complete digestion, as said before. During all these steps needed to convert the solid into a solution, make sure to avoid contamination. Then there are 3 steps that are done to get from a soil to a solution. First, the sample preparation, of course, the sample digestion, and finally, the preparation of the ICP-OES solution. Always make sure you wear safety glasses, a lab coat, disposable gloves, and in case of when you have to do a lot of milling, make sure you have a dust mask. The sample preparation. You have to take a subsample of the soil that is offered to you. It has to be representative. It also has to be dried, preferably oven dried at 105 degrees centigrade, because we want to report all our results in dry matter. When you use the oven, it is necessary to have a periodically verification of the oven temperature for quality assurance. After the drying of the samples, they have to be milled. And there are different materials you can use to mill the samples: agate, zirconium oxide, tungsten carbide. Make sure that when you use one of these materials, you don't have to measure them, because when you measure in zirconium or tungsten, they contribute a lot of the zirconium content and tungsten content of the samples. Make sure also to clean between samples with water, but also grinding with sand, glass, or even rice helps cleaning the vessels. Here you see some photos of how it's done in our lab. So we did the milling in vessels coated with zirconium oxide. You see the dried coarse sample that is placed in the ball mill. A few minutes clockwise, counterclockwise are sufficient to result in a fine homogenized result, ready to do the digestion. So the sample digestion, you take about 0.5 to 1.0 gram of dried and grind sample, and you weigh it into a digestion vessel. We use disposable digestion vessels with ICP-MS grade polypropylene, because the contribution of the elements of interest are minimum with this ICP-MS grade polypropylene vessels. And these vessels are also calibrated to 50 ml. We use also disposable micro spatula to weigh in the sample. Don't forget to record the sample identification, the actual weight, and the position you're going to place the digestion vessel into the digestion device. Also make sure that the balance you use to weigh these samples is periodically verified and at least once a year calibrated by an accredited calibration company, this for quality assurance. The next step in the sample digestion is to add the acids. In this case, we're going to use aqua regia. So 2 ml of nitric acid and 6 ml of hydrochloric acid. These acids must be added slow because you're working with acids by a suitable dispenser or a mechanical pipette and corresponding disposable tips. Of course, you work under a fuming hood. In the choice of purity of the acids, we also prefer ICP-MS grade. So the presence of elements of interest is non-existent or negligible. Then allowed to react at least for 30 minutes. If a more intense reaction is observed, you have to increase the reaction time under the fuming hood. When you see there is no reaction left, you can close the digestion vessels with appropriate, also ICP-MS grade polypropylene screw caps, and you can place these digestion vessels in the heating block. Also, the ICP-MS grade polypropylene is necessary. You don't have leachment of elements of interest into the solution. Very important is to loosen the screw cap half a turn, so you can avoid pressure buildup and even a possible explosion of the digestion vessel. But still, the evaporation during the acid digestion is minimum. Then finally, you can start a digestion. So as set, 120 minutes at 105 degrees centigrade. Make sure you use a slow RAM time. The RAM time is the time necessary to reach the ultimate digestion temperature of 105 degrees, and it needs to be slow so you can give the sample time to adapt to the temperature and to control reaction. The digestion block is placed under a fuming hood, or like this, in this case, forced extraction is used. At the end of the digestion, you have to allow the samples to cool down to room temperature, and then you can make up the digestions with ultra pure water, and you homogenize them. Because we use disposable polypropylene digestion vessels with a certified marker at 50 ml, we can easily make up the samples to this marker. So the result you have now is a liquid, and like you see here, there are still some solids present in the digestion solutions. These solids need to be removed from the digestion solution because it can cause a blockage of the ICP-OES introduction system. There are 3 ways in which you can get rid of these remaining residue. First, simply use gravity, allow to settle overnight, at least overnight. And then you can use the clear solution above. Or if the analysis need to be done in a hurry, you can use centrifugation. For this, you have to transfer the digestion solution into a disposable centrifuge tube and use centrifugation forces to obtain a clear solution. Again, when you use these disposable centrifuge tubes, make sure they are of high grade, so no elution of elements of interest is present in the centrifugation tubes. Finally, you can also use filtration by using a disposable syringe and a 0.45 micrometers syringe filter to obtain a clear solution. So here you see some photos of how we have done this in our lab. The centrifugation before and the cleared solution after. Gravitation, you see the settled residue at the bottom of the digestion vessels. And finally, centrifugation, filtration by using a syringe and a syringe filter. So together with the unknown samples, there are also a number of quality control samples that also should be included in the digestion procedure. First, of course, a procedure blank that is actually not a real sample, but goes through the entire digestion process. And it's used to map contribution of materials and reagents to trace contamination. These procedure blanks can also be used to determine the limit of detection and the limit of quantification. Best is to use a procedure blank for every digestion batch you do. Next, you also need precision samples. This is basically the analysis of a sample in Duplo, so a replicate analysis. Or you can also use in-house made laboratory control sample you analyze at regular intervals. An accuracy sample is also needed. This is a certified reference material that you can commercially buy. Also needs to be analyzed at regular intervals. And finally, make sure you participate on a regular basis on round-robin tests or proficiency tests. So finally, you will end up with a solution that is ready to measure by ICP-OES, and you can fill your autosample rack with these solutions. So this concludes the preparation of the sample, so the digestion of the sample. The next step is to the actual ICP-OES measurements. So I will try to give you an overview of the actions that are necessary to determine the concentration of the elements in the prepared digestion solutions by ICP-OES. Whatever brand ICP-OES you use, these actions to get a good result remain the same. Make sure to wear safety glasses, a lab coat, and disposable gloves. After all, you're still working with assets. And when you use an ICP-OES, make sure to do an annual checkup and maintenance by the brand field engineer to ensure the optimal working of the ICP-OES. So what is now this ICP-OES workflow? First, you have to follow a startup checklist to get the ICP-OES ready to light up the plasma. Then you have to set up a measurement method. That is mainly software that you have to program. Then you start the measurement sequence. After, at the end of the measurements, you have to do some post-measurement evaluation. Also evaluate the QC measures, and hopefully you will get result. So this startup checklist. First, a cooling unit. You have to start it. A cooling unit is necessary to cool the detector. Also, the RF generator needs to be cooled and the RF coil. The cooling unit needs to be in working order only when the ICP-OES is working. Make sure there is enough cooling fluid present in the cooling unit. Start up the autosampler. Check the rinse solution level. Make sure there is enough rinse solution present to do the analysis you are planning. Check the state of all tubing present on the autosampler. Also check the state of the sample needle. Make sure there are no, how you say it, some Yeah, it's broken. Make sure it's not broken. And also check the mechanism to fill the rinse station. Then do a check of the argon. The argon is necessary to generate plasma, but also to work the nebulizer and to purge the optics of the ICP-OES. Make sure the pressure is within specs, and make sure there is enough argon present to do the analysis you planned, especially when you're working with argon gas bottles as opposed to a tank. Then also important, check waste containers. Make sure there is sufficient capacity for the waste you're going to produce during the whole analysis. The waste that is produced is mainly produced by the drain of the spray chamber and the rinse station of the autosampler. Make sure your waste containers are placed on a drip tray. Then check the extraction airflow rate. Make sure it is within specifications. This extraction airflow is mainly used to vent the torch and plasma compartment. Then important piece you have to check is the sample introduction system. One of the most important things in this system is the peristaltic pump, and it has to have minimum 3 channels. It has to have a channel to drain the spray chamber, a channel to pump the internal standards, and a channel to supply the sample from the autosampler to the nebulizer into the plasma. The internal standard tubing and the sample tubing, they connect in a Y-piece and they get mixed to go to the nebulizer. Make sure you change this tubing regular, because this tubing gets worn out or it gets stretched out and gets flattened by clamping it onto the pump. Make sure to check all connections to prevent leakage, especially when you are changing the pump tubes. Now you see a video of the drainage of the spray chamber. You see a segmented drain. So the drainage of the spray chamber is sufficient to make your aerosol. Now some more explanation about the internal standard. What is an internal standard? It's a solution of elements that are not or negligible present in the samples. Common used are yttrium, rhodium, ruthenium, scandium, indium, germanium. These solution of elements at high concentration, 1 to 10 micrograms per liter, and they are pumped and mixed online with each measurement in a ratio 1 to 5. Now, how we determine this ratio? It's simply by taking a different internal diameter of the sample tube and the internal standard tube. So the internal standard tubing will be 5 times, the internal diameter will be 5 times smaller than the sample tube. Then the sample and the internal standard are mixed. So here you see mainly internal standard. Then you see the pumping of the sample, and together they are mixed and they will reach the nebulizer. The next in the sample introduction system is the nebulizer. It is needed to turn the sample solution into an aerosol. the sample solution is pumped through an inner capillary, here and here, inside the nebulizer. This capillary is surrounded by high flow of argon. These two flows, the sample flow and the argon flow, meet at the tip of the nebulizer. The sample flow is broken up into an aerosol. The most common used nebulizer is a quartz glass concentric nebulizer. An alternative is a inert nebulizer with a higher internal diameter for when you work with high total dissolved solids or a very high acid matrix. Here you see the working of the nebulizer. You see the formation of a fine aerosol. It's like a fine mist. And you also see the drainage of the spray chamber. So every excess of aerosol that doesn't reach the plasma is drained away. Together with the nebulizer, the spray chamber is necessary to select only the smallest, most uniform aerosols to reach the plasma. In the spray chamber, there is a cyclone created that centrifuges down the very large aerosol particles, and only the very small aerosol particles will reach the plasma. This effect can be enhanced when you use a baffled spray chamber, and a baffle is just a small glass channel that is placed in the middle of the spray chamber, so even smaller aerosols reach the plasma, making sure that you don't have an overload of the plasma and you have a very stable plasma. These are the most two common types of spray chambers, thus the quartz glass cyclonic spray chamber. An alternative is an inert baffled spray chamber, again for use with high acid matrix and high total dissolved solids. The final part of the sample introduction system you can find inside the plasma compartment. And inside the plasma compartment, you find the torch. It consists of an outer tube that is typically quartz glass. Make sure this torch is not damaged at the tip, because it's sometimes common to get damage at the tip. And an inner tube that is called injector, and it's also typically quartz glass with an internal diameter of 1.2 to 1.5 millimeters. Also in the plasma compartment is the RF coil or plates, depends on the brand of ICP you use. And the interfaces to the optical compartments are also present. By that we mean the axial viewing channel or the radial viewing channel. Also a part of that you can find in the plasma compartment is the plasma top of tail plume cutoff system. So the top of the plasma is cut off because this is a cooler zone of the plasma where the formation of molecular emissions happen, and these can cause interferences. In this cooler zone of plasma, also absorption of earlier emitted light can happen. And cutting off the top of tail plume also prevents possible penetration of dirt into the optical part of the ICP-OES. Now there are two main systems to cut off this plasma top. You can make use of a cone that basically splits open the plasma tail plume, or you can also use a shear gas system that blows away the top of the tail plume, and that shear gas can be simple compressed air or nitrogen. An alternative for the quartz glass torch or injector is a ceramic torch and injector. This injector have a larger diameter, so also for use with high acids and high total dissolved solids. Here you see some insides of the plasma compartments with the torch, the different types of torch, a ceramic torch. These are all quartz glass torches. Here you see a ceramic injector with a larger diameter. Here, I don't know if it's very clear, you can see a quartz injector. Also, the viewing channels, the radial, the axial, axial, radial, axial, and the radial, and here the radial and the axial, and the different tail plume cutoff systems, a cone, like here. This is also a cone, and this is also a cone, and this is the only brand that uses air to cut off the tail plume of the plasma. And finally, when all these checks are done, you can light the plasma. After the plasma is lit, the values of the RF power, the auxiliary argon gas flow, and the plasma argon gas flow are usually brand specific and are mostly not optimized. What needs to be optimized is the nebulizer gas. And it must be optimized together with a pump speed for each new type of nebulizer you use. So you don't have to do it every time, but every time you use a new type of nebulizer, you have to optimize this type of nebulizer. And you can do this by making a solution of elements and nebulize it. Perhaps the elements that have a low sensitivity in ICP-OES, for instance, arsenic or selenium. And then you play with the neb gas flow and pump speed. And you select the settings that have the best sensitivity for these low sensitivity elements like arsenic or selenic. Then during the plasma ignition, make sure that the autosampler needle is in the rinse solution and the internal standard tubing is pumping the internal standard solution, so you don't run dry. Make always sure that there is a sample going into the ICP-OES. Allow the plasma to stabilize for about 20 or 30 minutes before you start a measurement. Important is also a daily check of the sensitivity of the ICP-OES. You can do this by measuring a mix of elements of your choice. For instance, again, arsenic and selenium, or you can use even the internal standard solution, and you can compare these sensitivity of these elements by previous measurements of these elements, maybe the day before or the measurement before. This gives you an indication if you need to do some maintenance on the ICP-OES. For instance, clean the nebulizer, the torch, or the windows to the optical parts, fit new tubings, and so on. So finally, the sample is transported by the autosampler to the plasma. The internal standard solution is transported through the Y-piece, the peristaltic pump, and mixed with the sample. Then this mixture goes to the nebulizer and the spray chamber. Aerosol is formed. The spray chamber is properly drained, and the aerosol goes finally into the plasma. So now we have to program or tell the software of the ICP-OES what to do. The first step is to select the elements of interest. So per element, you select multiple wavelengths from a predefined list. Multiple wavelengths, why? To trace spectral interferences. And in case of a spectral interference, you have always an alternative wavelength to turn to. Make sure that besides the elements of interest, you also select extra elements, so you get a more complete idea of the matrix composition, and also you can trace possible interferences. In this step, also the elements used as an internal standard has to be selected. Keep in mind that ICP-OES is a simultaneity technique, so adding extra elements and wavelengths are negligible in measuring time. And the most brands of ICP-OES, there is not a possibility to add wavelengths after the measurement. So what is not measured, you don't have results, and you have to measure again. Then the second step in the measurement method is to define some acquisition parameters and some conditions. First, you have to choose which view mode you're going to use. The axial view mode, so you can view the entire analytical channel. It provides the best intensity and the lowest limit of detection, but also the highest chance of spectral interference. You can go for a radial view mode. This is only a small region of the plasma that is viewed, which region that can be optimized depending on the elements you want to measure radial. Drawbacks are a higher limit of detection and lower sensitivity, but also low spectral interference. It is also possible to do a combination of these two, axial, some elements measured axial, other elements measured radial. Furthermore, you have to select the number of replicates, that is the times a sample is measured per view mode. We always go for 3 because it is a good consensus between quality, it provides good statistics, and time, because every measurement takes time. And the next thing you have to do is also set the measuring time per replicate per view mode. Typically, axial view mode between 10 and 25 seconds per replicate, radial view mode 5 to 15 seconds per view mode. So when you have a method in which some elements are measured axial, other are radial, and you have 3 replicates, exposure time for axial 25 seconds and for radial 15 seconds, it comes down to 120 seconds total exposure. You have to keep that in mind, that you have sufficient sample in your autosampler to get this measurement done. Then it is also necessary to select a take-up time and a wash time. Take-up time is the time the sample needs to travel from the autosampler to the plasma. Also take in account some time to let the sample stabilize in the plasma. It depends on the pump speed you selected and the internal diameter of the pump tube, but about 60 seconds should do the trick. Then also important is the wash time, the time you need to wash out all elements after the measurement is done, so no cross-contamination occurs. Typically 60 to 80 seconds rinse solution should do this nicely. Next, you have to indicate which of the elements and wavelengths are used as an internal standard. And you can also, at this stage, couple the internal standard wavelength to an element wavelength. You can also do this later on after the measurements are done. Finally, we also need some parameters that concern the calibration curve. Of course, the curve type has to be defined. It's always linear. So you have to be sure that the calibration curve covers the linear area of the concerned wavelength. And a rule of thumb is to force the curve through zero. The next step in the measurement method is the definition of which calibration standards and QC samples you are going to use. First of all, the calibration blank, always matrix matched, and use the same ICP-MS grade purity of acids that is used to do the digestion. All materials you use to prepare the calibration blank should be contamination free. Then the actual calibration standards. The calibration curve should consist out of a minimum of 4 standards per element to cover the selected calibration range. It is also matrix matched.
I think we lost Philip for a while. Hello, Philip, can you hear us? Hello, Philip?
Yeah.
We lost you for 10 seconds,
okay.
But you're back now. Okay.
Okay. Then I will start again with the calibration standards. So as said, we need a minimum of 4 standards per element to cover the calibration range. These calibration standards should be matrix matched, same grade purity of acids as used for the actual digestions. Then they are made out of a mix of commercially available mono multi-element solutions that are mixed together, but make sure that they are compatible and stable when you mix them. No precipitation can occur. And also check the compatibility of these mono and multi-element standards with the acid matrix, in this case, the Aqua Regia. All materials that are used to prepare these calibration standards should be contamination free, of course. Then you also need to define and make some calibration check solutions. These are used to check the validity of the calibration. Making these calibration check solutions, the same remarks apply as for the calibration standard itself. Matrix matched. It's a mix of commercially available mono multi-element standards, but the difference is they need to be of a different manufacturer from the calibration standards. So you have an independent check of the calibration solution. of the calibration curve. Also check if they are, when they mix together, they are compatible and stable, and there are no precipitation formed. So multiple calibration check solutions may be required. Of course, all materials used to make this calibration check solutions should be contamination-free, and try to aim at 2 different concentration levels per element. Then finally, we also need a blank check solution to check for cross-contamination between samples. This is basically a remeasurement of the calibration blank solution. And finally, some drift control samples to check the long-term stability of the ICP-OES. And they are usually a remeasurement of the calibration standards with the highest concentration. And the drift control samples can also be used to check if the ICP internal standard compensation is done correctly. So for all these calibration blank standards QC samples, you have to define which elements are present, in which concentration, and which is the unit. Then final step before we can start our measurements is to make the measurement sequence. Which info should be present in this measurement sequence? It defines the order in which the different solutions are measured, or have to be measured. So it always have the same structure. It also needs to contain data to calculate the final concentration, that is possible dilution, the sample weight and unit, and the final volume and unit. Also, you need to define where to find the solutions in the autosampler, and perhaps define an end action. What must the ICP-OES do after all the measurements are done? You can program it to shut down the plasma and the pump, or you can keep it running to start a new measurement sequence. As said, the structure of the measurement sequence is always the same. Best is to start with some rinse blanks to clean the system and condition the plasma a bit. Then you measure the calibration blank, followed by the calibration standards in increasing concentration, followed by the blank check solution, the calibration check solutions to check the validity of the calibration. Then if you're going to use inter-element correction, you need to also measure the solutions necessary to do this correction. And then the procedure blank is measured. And then a number of samples and the possible dilutions are measured. You end with, again, the measurement of the blank check solution to check for cross-contamination, followed by the drift control samples. And then you can repeat steps 8, 9, and 10, indefinitely, as long as the drift control samples and the blank check solution check out, you can repeat this steps. Then finally, we are ready to start the sequence. And then you can have a cup of coffee. And when you come back, the results are ready to evaluate it. So at the end of the measurement sequence, when all the results are collected, there is still some work to be done. Now the evaluation phase can begin. So a thorough evaluation of the results is necessary. It is necessary to inspect the spectrum of every wavelength used. What I mean with the spectrum is what you see here. You have to adjust the peak maximum position. That is the green cursor here. You make sure it is on the top of the element that is measured. And you have to also select background points left and or right, preferably left and right. And you also need to do some inspections for spectral interference. The main goal is to end up with at least one perfect wavelength per element. So here you have some examples of spectra. You have to determine the peak center of every element, the green bar. Make sure it is at the top of the element that is measured. Then you have to select a background point, left, and preferably left and right. These are the blue bars. You have to avoid, in setting these background points, avoid interference of other elements. The signal that is used is when you connect the left background point and the right background point. So the signal used is measured from this line until the top of the peak. These settings, they apply for all measured solutions for the concerning wavelength. So you can't select different settings for each sample separately. Some practical examples of possible errors that can occur. In the first spectra, you see a wrong setting of the left background point. It is set on what is suspectedly an interference. So when the line between the left and the right background point is drawn, you see that the signal used is an underestimation of the real signal. The second spectra, you see there is barely impossible to find a good background point on the left. So it is discarded, but basically this is a wavelength that is not usable, especially in an iron matrix, as this is an iron interference. And finally, the third spectra, the right background point is best discarded, because if the silicon interference you see here increases, it becomes impossible to set this right background point. And in this case, by discarding the right background point, you can still use this wavelength in a high silicon matrix. So this evaluation, as said, has to be done for each wavelength. Keep only the wavelengths that make sense. Discard all not usable wavelengths. Save all settings of peak center and background points. And this way you can create a template that can be used for future samples or future measurements. As long as the environment, the ICP-OES, is stable, that means if the temperature is stable, so you don't have a drift of the peaks. All the samples you are going to measure are somewhat similar in composition, and you use the same acid matrix. You can use this template, and afterwards, only a quick check of the spectra and not a thorough one is sufficient. So you can speed up your workflow. Then after the evaluation of the wavelengths and the settings are optimized, the final quality controls can be evaluated. The calibration curve correlation coefficient should be bigger than 0.995. Then the calibration check solutions to check the validity of the calibration curve should be within 10% of the theoretical value. The procedure blank solution, the concentration should be less than half the limit of detection, or at least less than 10% of the concentration of the elements of interest in the unknown samples. Should this check fail, this means you have had a contamination during analysis. You must identify the source of this contamination, and even a complete reanalysis, including digestion, can be necessary. Then the reanalysis of the calibration blank standard to check for cross-contamination. The same rules apply as the procedure blank solution, so the concentration should be less than half the limit of detection, or at least less than 10% of the concentration in the unknown samples. As said, fails means that there is a cross-contamination during analysis, so you have to adjust your rinse time or even your rinse solution. The drift control samples at the end of a sequence should be within 10% of the theoretical value. Then evaluation of the internal standard. Recovery should be within 70 and 130%. If this fails, check if maybe the internal standard element is present in the samples, mostly with recoveries over 100%. This is a case. Also check if the failure of the recovery is due to spectral interference. If it's not the case, you have to dilute the sample until the internal standard recovery is within these limits. The selection in which internal standards to use for which element is based on spike addition of the sample at half calibration curve value. So you have to have a recovery of the spike between 85 and 115%. And then you select the internal wavelength that gives you the best analyte recovery. This means that sometimes no internal standard correction is necessary. In case you use dilution of samples, you have to do the dilution check. There can be no more than 10% difference between the diluted and the undiluted sample. If it fails, maybe you made a dilution error, just make the dilution again, measure it again. Or the difference can be due to a matrix effect. This needs further investigation of the spectra. And the preference is to report, if possible, the diluted measurement. Then finally, some words about the internal, inter-element correction solution. This is a solution that contains the analyte element and the interferent elements in about the same order of magnitude as the unknown samples. In this solution, the recovery of the analyte element after the inter-element correction should be within 10% of the theoretical value. Iron is an important interferent that is significant present in soil. So if you measure in pure iron and inter-element correction solution containing iron and the interfered components, you get a long way. An example of this is the interference of iron on the cadmium-214 wavelength. If you look at the spectra, you see an overlay of a pure cadmium solution, a pure iron solution, and a sample that contains cadmium as well as iron. You see the shift of the peak. The peak, there is no overlap in peaks between the pure cadmium and the sample cadmium. That means there is a interference present, and in this case, it is iron. So if you don't use inter-element correction, you will have an overestimation of the cadmium concentration because the result is due to cadmium and iron intensity. So how to tackle this? So you make sure you measure a pure iron solution, and you measured it on the cadmium-214 wavelength. This results in a certain intensity due to iron and not due to cadmium. You calculate, or the software calculates, an inter-element factor. The next step you have to do is to measure the correct iron concentration in this sample. And finally, you can measure the sample on the cadmium-214 and then use the inter-element correction factor. You calculate it together with the real iron concentration. Then you calculate an estimation of the contribution in intensity of iron on cadmium-214. You subtract that from the intensity of the sample, and you have the real cadmium concentration. Don't be afraid, all calculations are done automatically by the software. You don't have to do them manually. So, and when you have done all these steps, finally you will have results and you can report the results. So I thank you for your attention. Should there be questions?
Okay, thank you very much, Philippe, for this real nice and detailed overview of the different steps of an ICP. So the ICP measurement, it's only 2 minutes, I guess, but there is a lot more to be considered, and you explained it very well. Are there any questions? I can already see that indeed there was an answer from the Ukrainian Laboratory of Quality and Safety of Agriculture Projects, stating that they use flame AES for mobile forms of heavy metals, ICP-OES for measuring of the total content, just like you explained. And they also have an ICP-MS for arsenic and mercury determination. I see indeed arsenic, you also mentioned it, Philippe, that the optical is not so sensitive, I think, for arsenic and selenium. Considering, I think, 1 gram of soil, what is more or less an estimated detection limit for soil, you would say? You're sorry, Philippe, you're muted.
I will do some calculations.
Yeah.
Yeah, I
Meanwhile,
think about 0.5 ppm,
yeah.
0.5 milligrams per kilogram
Yeah.
is feasible, providing you use 1 gram into 50 ml.
Yeah. And I think as well, you can confirm, you showed that we have 4 different ICP-OES instruments in our lab available.
Yes.
And I think we see that also the last years, the sensitivity keeps on improving of the instruments. So they're always getting more sensitive. Yeah. So I think also in the future, we can even expect that maybe better. Are there any other questions on this topic? Yeah. I think you explained it very well, Philippe. So, and I think within, I think it's exactly 2 weeks, more or less, you will give this practical training as well then, starting from the digestion to the determination, covering all the different steps. So if there are no more questions, I propose to end this session. And then I expect all of you to be present within, I guess, more or less 2 hours for the last session on the determination of explosive and propellant residues. So thank you once again, Philippe, for your explanation, also to all the attendees. And I see you within 2 hours. Thank you.